And I'll start the recording. Okay, so we want to use a power series to approximate this integral correct to 6 decimal places. Let me give you a moment to copy the example down. Okay, Julia had a good question about when the announcement will come out. So, good question, Julia. So I plan to get the announcement out like after my office hours today. I plan to work on the announcement and get it out this afternoon. So it should be out sometime between 3 and 4 o'clock. Okay, and I want to get it out as soon as I can because I know that you're that some of you are interested in starting the exam tonight. So absolutely. You're welcome. You're welcome, Julia. All right. Okay, one moment here. Just one moment. Okay. Okay. So we want to use a power series to approximate this integral correct to 6 decimal places. And this integral, of course, the question is, how are we going to use the Apple formula that you learned to express this log of 1 plus x to the 4th as a power series? Well, remember yesterday we had a problem dealing with the arctangent. And the arctangent by, let me just, right, the arctangent, what we did was we said the arctangent was the integral of 1 over 1 plus x squared dx, and then we were able to write the 1 over 1 plus x squared as a power series, and we were able to get an expression for the arctangent. Well, in the book, in the ebook, in example 6, we show how to find a power series for the representation of the log of 1 plus x. Now we have the log of 1 plus x to the fourth. But let me just show you here. Let me just show you. So it can be shown, and this is example 6, section 8.6, that the log of 1 plus x can be written as the power series starting in n equals 1 going to infinity of negative 1 to the n minus first power times x to the nth power over n. And the interval of convergence would be the absolute value of x less than 1. Or another way of saying that is that x is between 1 and negative 1. So the book in section 8.6 shows how to get this, shows you how they get this result. I'll let you look at that example to see how they get this result. But now, of course, what we have is log of 1 plus x to the fourth. So let me just write something down here. So we know we have this formula that we have a power series for the log of 1 plus x. So let me ask you, suppose I want a power series for the log of 1 plus an apple. And this apple, this is just, you know, I'm not trying to relate this to the previous formula you learned, you know, 1 over 1 minus the apple. I mean, well, but it's the same kind of principle. I have a power series for the log of 1 plus x. I want the power series for the log of 1 plus an apple. So of course, this power series for the log of 1 plus apple, it would follow that it would equal the sum from n equals 1 to infinity of negative 1 to the n minus 1 power times the apple to the nth. I'm trying to write this the best I can. It's not easy. But apple to the nth power all over n. Apple to the nth power all over n. And of course, the restriction on the domain would be that the absolute value of the apple is less than 1. So does this formula, I mean, I want to say it's the right way, based on this established formula for the log of 1 plus x, the established power series for the log of 1 plus x, does the power series for the log of 1 plus an apple make sense? Good. Robin's comfortable with that. All right. Are there any other folks that are comfortable? Good. Give a thumbs up if you're comfortable. Thank you, Josiah. Thank you, Julia. Excellent. Tyreek, thank you. Excellent. All right. Is anybody uncomfortable? You have to let me know if you have any questions. So all we're doing is, x is a variable, right? X is a variable in the log of 1 plus x. X takes on different values. I'm just treating the apple like a variable, okay? Okay, and so it follows that the log of the 1 plus apple would have to be the sum of -1 to the n minus 1 times apple to the nth power over n. Okay, all right. So we had 4 students who are comfortable with that. Might I see a few more thumbs up if you're comfortable with that? Good, thank you, Daryl. Good, John, that's Stella, excellent, excellent. Thank you. All right, so, well, okay. We want the power series for the log of 1 plus x to the 4th. So x to the 4th I'm going to treat like my apple. And therefore, the power series for the log of 1 plus x to the 4th would be just the sum, where n equals 1 to infinity, of -1 to the n minus 1 power times x to the 4th raised to the nth power over n. The x to the 4th is my apple. Okay, so it's like you can make use of the established formula for the log of 1 plus x and just replace the x with x to the 4th. The x to the 4th is your apple. And so that allows you then to get a power series for the log of 1 plus x to the 4th. And of course, the interval of convergence has to be such that the absolute value of x to the 4th is less than 1, right? Because this is really a geometric power series. And so that means then the absolute value of x is less than 1. So x would fall between -1 and 1 for your interval of convergence for this power series representation of the log of 1 plus x to the 4th. Okay, are there any questions on this? All right, so now, like as another example, in your exercises, you have a problem that involves an arctangent of, I believe, 3x or 2x or 4x, but let's say it's an arctangent of 3x. Well, to find the power series for the arctangent of 3x, just take the power series for the arctangent of x and replace the x with 3x. And that'll get you the power series for the arctangent of 3x. That's how you handle that situation. Okay, are there any questions before we move on? We still have to solve our problem here. We want to find power series approximation. Well, we want to use a power series to approximate the integral from 0 to 0.4 of the log of 1 plus x to the 4th dx, correct to 6 decimal places. So, all right, we have our power series for the log of 1 plus x to the 4th. So then naturally, the integral of the log of 1 plus x to the 4th dx will be the integral of that power series. Now you'll notice that I'm not working with a definite integral. So normally when I have a definite integral, I don't drop the limits. I work with I like to keep the limits there and work with that definite integral. But in this case, it is a little easier since there's kind of a lot of stuff going on. It's a little easier just to get the power series for the indefinite integral and then work with the definite integral a little later. So let me see. Oh, I think I left one step out. Hold on. Let me check one thing here. Yeah, I'm sorry. I thought I was missing something. So of course, we have the power series for the log of 1 plus x to the fourth. And so now we want to get the power series for the integral of the log of 1 plus x to the fourth. And as I mentioned before, normally with a definite integral, I like to carry my limits and not I like to carry the limits along, and then if I do a u substitution or something, I change the limits and I got new limits. But in this case, because there's a lot going on, it's easier just to work with the indefinite integral of the log of 1 plus x to the fourth, get the power series for the indefinite integral, and then work with the definite integral later on. So the integral of the log of 1 plus x to the fourth dx is the integral of its power series. And the integral of a sum is the sum of the integrals. So that gets us to this stage right here. Let me just ask you, class, when I take this, when I take the pages of the notes and I blow them up and so forth, do you see that too? I mean, you see, like when I underline things in blue or red and circle things, you see that, right? Because that's in the recordings. But when I'm just asking as a, like when I like in the live class session here, like when I zoom in and zoom out, do you see that also? If you could just let me know. Okay, Josiah says no. Okay, all right. So, okay, thank you, Tyreek and Robin, also for the input. So, but you do see me underlining things in. Oh, Maxim says you have to do that individually. Okay. Okay, so the underlining, you can see that. But then, all right, then as students, are you able to blow the pages up like if you're like I'm here and I'm underlining things in the notes? Okay, so John says yes. Josiah, great. So you're able to blow the notes up. Toolbar on the left side. Okay, great. Thank you. It's just curious from a student's perspective. Wonderful. Okay, so now what do? We continue with the problem. All right, I'd like to move to the next slide. Are we good so far? Okay. So then here's where we were. The integral of the log of 1 plus x to the fourth dx is the sum of these integrals. And -1 to the n minus 1 over n we treat as a constant because the integral is with respect to x. And so we factor the -1 to the n minus first power over n out. And now we have the integral of x to the 4nth power, and we get the antiderivative. And this is where we have the plus constant, because this is a power series representation for this indefinite integral. So all right, are there any questions up to this step right here? Okay, okay. So now we're ready to get our approximation for our definite integral. So what I do is I say, okay, all right, so I take the power series. Of course, now we have a definite integral, so we don't have that constant anymore. But what I do is I write out the first 4 terms of the power series. And of course, we are integrating from 0 to 0.4. Notice that 0 and 0.4 are within the interval of convergence. So you have to make sure that, I mean, the limits have to fall within the interval of convergence in order to use a power series to approximate the integral. So like, for instance, if you had the integral from 0 to 7, okay, that you couldn't use power series approximation for that. Well, I want to say you couldn't use a power series approximation based on section 8.6 to approximate an integral from 0 to 7. You'd have to use something like numerical integration, like Simpson's rule or a midpoint rule. I mean, that's one way, right, to do it. But all right. So what do you notice about this series here? We have plus x to the 5th over 5 minus x to the 9th over 18 plus x to the 13th over 39 minus x to the 17th over 68. Okay. Is everybody okay with the terms, the first 4 terms of the series that I wrote out? Is everybody okay with that? Okay. So what kind of series is this? I have a positive term, and then a negative term, and then a positive term, and a negative term, a positive term. What kind of series is this? Series goes positive, negative, positive, negative, positive, negative. What kind of series is that when the terms are alternating in sign? An alternating series. That's right, Josiah. So that means that we can use the alternating series estimation theorem to help us get this approximation. Okay. And the point 4 is there, but I'm just going to write it a little bit. 0. Hold on. Let me clean that. I mean, it's there. It's there. It's on the paper. Just made it, but I just want to formally write it here if I can. Man, this is tough. 0. Well, top limit is 0.4. Okay. So, all right. I'm going to put in 0.4 into the series, and then when I put in, so I'm going to have the series evaluated at 0.4 minus the series evaluated at x equals 0, but we know that's going to be 0. So this is what we have of the series. The question is, when do we stop? When do we stop? Okay, well, if we want correct 6 decimal places, we have to look for the term in the series that's the, if we want this power series approximation to be correct to 6 decimal places, then we examine each term of the series and stop until we find a term of the series that's less than what? What number? being that we want correct to 6 decimal places. That's correct, Josiah. Excellent. 5 over 10 to the 7th power. And so that's what I do. That's what I do. So the first term here is 0.002048. Okay, that's the first term of the series. Well, that's not less than 5 over 10 to the 7th. The second term is 0.0000146. That's not less than 5 over 10 to the 7th. The third term, 0.4 to the 13th over 39, is 0.000000172. That's still greater. That's greater than 5 over 10 to the 7th. However, the fourth term, 0.4 to the 17th over 68, that's going to be, your calculator will give you 2.52 times 10 to the negative 9th. That is less than 5 over 10 to the 7th. That is less. And so therefore, we're only going to need the first 3 terms of the series to get the accuracy we need. Okay. So once again, 2.52 times 10 to the negative 7th power. That is less than 5 over 10 to the 7th. 5 over 10 to the 7th would be, hold on, give me one moment here. Okay, so that's, let me see here, hold on. I got to be a little bit careful here. I think actually well, this is what the solution in the book had, but I think the solution in the book is actually not correct. Let me check one thing here. I'm thinking that we only need maybe the first 2 terms of the series, because the 0.4 to the 13th power over 39 is, and let me just see here. It's worth investigating here. 0.4 to the 13th power divided by 39 is indeed 1.72 times 10 to the negative 7th. So that would be exactly what you see there. Now, let me just see here. Okay, so yeah, I think the book has an error, class. I think the book has an error. Let me erase this. Put this in blue here. I think this term here, the third term is actually less than 5 over 10 to the 7th power. So really, in my estimation, we only need the first 2 terms of the series then to get the approximation correct to 6 decimal places. So I think there's I think, you know, sometimes what happens is there may be graduate students that, you know, write, maybe, you know, they write out solutions to these problems, and maybe somebody was a little bit lazy. But I think you only need the first 2 terms. Let me check one thing on that. Yes, Nema agrees with me. Yeah, I think what happens is they get a little sloppy. Because you know, I mean, you know, both things can't be true, right? Both things can't be true. And let me just check one thing here. All right, one thing here. Let's see. Yeah, sometimes I see the book do one thing one way and then another thing another way. But let's say for now, I'll tell you what, for officially, I think only the first 2 terms are needed. But let's just go with what the book has, and we'll err on the side of caution and say let's use the first 3 terms. Okay. Then by the alternating series, not test, alternating series estimation theorem, we'll use the first 3 terms of the series. I mean, put it this way. If the first 2 terms of the series gives you the accuracy you want, then the first 3 terms of the series should as well. So officially, alternating series estimation theorem, officially it should be really the first 2 terms of the series, but you know, the book uses the first 3 terms of the series. Let me just check one thing on that before we move on. But nevertheless, I think this gives you the guidance you need to be able to do this kind of problem. What I would say, so of course, when you are doing your, like you're going to see problems like this on part 2 of exam 3. And when you get your approximation, you can't just give me the approximation. You have to apply, like for instance, the alternating series estimation theorem. Okay, that's an important part of your work. So basically what I'm saying is, if you work the problem out, okay, okay, and then you need to include this part. You need to include this part here, okay, in your work to get full credit. And you know, it could be, you know, maybe half the points, I don't know. But showing this work where you're applying the alternating series estimation theorem by evaluating each term, okay, and then seeing which term is less than, in this case, 5 over 10 to the 7th power, and then stopping there. that's an important part of your work, and you do need to show it to get the full credit for the problem. And it's an important part of the work. Okay, so I don't know how many, like for a 10-point problem, would it be 5 points? Would it be 4 points? 3 points? I'm thinking it would have to be at least 3 points and maybe 4 points. So don't forget to show that. Don't forget to show that work. Okay. I want it to be, Josiah, exactly the way I'm doing it. Okay. Very good question. Josiah's asking, is there flexibility? Well, I mean, this has to be shown, right? Where you're checking each term to see if the term is less than 5 over 10 to the 7th power. That has to be shown. And so I'm showing it this way, but in what I would say then, Nema is asking the question. The correct answer is you'd only need 2 terms. So like in WebAssign for this kind of problem, it should accept the answer with just the first 2 terms. However, because the WebAssign problems might be, maybe for this problem they had it 3 terms. Maybe they just said, yeah, use 3 terms. Well, maybe then to get the answer in WebAssign, you'd have to use the first 3 terms. But what I'm saying, but that's actually a very good question. So what I'm going to do in WebAssign is for the second part, the answers themselves don't count anything towards for part 2 of the exam, where you show your work and upload your work. The answers themselves don't formally count as part of, like, I want to say this the right way. Yes, it's good to put in your answer and then WebAssign marks the answer correct. However, I look at the work, and the credit comes ultimately from the work. So, like for instance, if in WebAssign you have a problem like this, and you say, well, I only need the first 2 terms of the series, but yet WebAssign won't take your answer for the first 2 terms. I still, when I look at the work, can override WebAssign. Okay, in terms of that. So, but what I would recommend, I'm going to be, I want to say this the right way. In the problem itself, it says approximate correct to 6 decimal places. Okay, so yes, we only really need 2 terms of the series, but it doesn't do any harm putting in 3 terms of the series. Okay, it doesn't do any harm to put in 3 terms of the series. Okay, so if you do that, if you overshoot, put it this way, if only 2 terms of the series are needed, but you put in 3 terms of the series, that's okay. That's okay. I'm not going to take off for that, but you need to justify everything you're doing by showing how to apply that alternating series estimation theorem, like I show you here. Okay, does that make sense? Are you comfortable with that? Maybe give me a thumbs up if you're comfortable with what I just said there. Okay, great. Thank you, John. Thank you, Robin. Thank you, Tyreek. Thank you, Julia. Excellent. Thank you, Sachi. Thank you. And I saw that Nema had a question about, I think it was, yeah, okay. So Nema says WebAssign used 3 terms. Okay, that's fine. Okay, great. So okay, on that note, now I think you're going to be in better shape for for finishing the section. Let's see. Nema says if it marks you wrong, will you get the point back if you do 2? No, on when I grade your when I grade your work on the exam, you know, if you only need 2 terms, and then if WebAssign marked you wrong, I would override WebAssign in terms of the answer. However, there's nothing wrong with, you know, if you say, okay, 2 terms is enough, but oh, WebAssign's not accepting that answer. Let me go out 3 terms and let me see if WebAssign accepts that answer. There's nothing wrong with that. Okay? Is that, I mean, there's nothing wrong with that. Okay, you're welcome. You're welcome, Francesca. Excellent. All right, so I think now, having covered this example, you should be able, if you had difficulty on your Section 8.6 exercises that were due today, I think now you ought to be able to finish those off fine. And remember, you can get the extension for the Section 8.6 exercises due today. You can take the extension, and they'll be due then tomorrow at 11:40 a.m. And I'm not any deductions on points for taking the extension for the Section 8.6 exercises that were due today. So essentially, it's like, if you want, it's like you're getting an extra day to complete them. Okay, let me stop the recording.